Hello, this is Cubey, a hypersonic missile traveling at Mach 10. Russia's Oreshunik, or its successors, were the saturation drone swarms now visible in Ukraine in the Iran war. Thousands of low-cost machines arriving simultaneously. The arithmetic of conventional defense has broken. A defender firing a single Patriot interceptor, roughly $4 million per shot, against $1,000 drone is, by any reasonable accounting, already defeated. There is a possible response. It depends on two things rarely discussed together. A category of material science that only a few civilizations have the depth to assemble, and a philosophical disposition that does not interpret the world primarily through binary opposition. This is a final episode of a six-part structural inquiry that begins at the start of the Iran war. The subject is what I will call, deliberately and without theological connotation, the strategic neutrality shield. The strategic neutral shield is not a sword. It is a system that physically insulates civilization from the negative feedback loop of a dualistic conflict so that genuine space for dialogue can be preserved. Think of the neutrality of the Delphic oracle, which functioned precisely because it could not be conscripted by either side of any conflict. The shield of light belonged to that lineage, not the lineage of the spear. Let us examine then what it would take to build such a thing.
The economics of contemporary missile defense are already untenable. A single Patriot interceptor costs roughly $4 million. The SM-3 Block IA is closer to $40 million. If an adversary launches 100 drones costing $1,000 each, the defender pays at least $400 million for the privilege of intercepting a $100,000 attack. The arithmetic is not stable for a decade, let alone a generation. The subscription analogy is exact. Western defense procurement is now structured as an open-ended subscription to consumables. Each crisis requires a new payment to the same suppliers in the same currency on terms set elsewhere. The system functions perfectly for the lessor. A laser interception system, by contrast, is closer to owning the building than renting it. The marginal cost of a single shot is electricity, perhaps a few dollars. The capital cost is high. The recurring cost approaches zero. Over a decade, ownership wins decisively, regardless of how the user feels about the analogy. But cost is not the entire argument. Drone saturation is not merely an economic problem. It is a physical one. Conventional missile defense, one launcher, one interceptor, one target, cannot keep pace with simultaneous arrival from many directions. A laser, given continuous power, can engage targets in series at the speed of light. It is the only known method that defeats numerical asymmetry without bankrupting the defender. This is why the question is now urgent rather than theoretical. In theory, light travels at light speed. A Mach 10 missile is moving at roughly 1,000th of that. A laser does not need to lead the target. If the targeting system can hold the beam on the target body for long enough, the geometry guarantees a hit. In practice, four physical obstacles stand between theory and a working system. First, heat tolerance and dwell time. A hypersonic missile is already designed to survive thousands of degrees from atmospheric friction. Burning through its skin requires concentrating very large amounts of energy on a single point for a measurable duration. Holding a coherent beam on a small, fast-moving, maneuvering target for that duration is not trivial. Second, plasma shielding. A hypersonic body generates a sheath of ionized air around itself. This plasma layer can absorb, scatter, or refract incident laser light, behaving as an unintended defensive barrier. Third, output insufficiency. Currently deployed and prototyped laser weapons operate at tens to hundreds of kilowatts, adequate for drones and small munitions, inadequate for missile bodies. The threshold for reliable kill against a hardened hypersonic target is generally considered to begin in the megawatt range. Fourth, atmospheric attenuation. Rain, fog, snow, and dust absorb and scatter laser energy. A system with several kilometers of clear weather range can drop to a few hundred meters in heavy fog. Weather, in other words, is not a footnote. It is a constraint that reshapes the entire system architecture. These four obstacles are not solved by incremental improvement. They require a different combination of technologies used in a different way. Two of those technologies are fusion and artificial intelligence. We turn to those next.
The four obstacles are addressable, not by extending current laser systems, but by combining with two technologies that change the underlying constraints. The first is fusion. Note before proceeding, because conflation matters here, the fusion is not fission. The two are routinely combined in popular discourse, and that conflation undermines this entire conversation. Fission is a runaway chain reaction that must be actively contained. If containment fails, the reaction continues. Fusion requires active confinement. If you stop supplying fuel or cease maintaining the plasma conditions, the reaction terminates within milliseconds on its own by the laws of physics. This asymmetry is not a marketing point. It is a structural property that determines what kind of weapons a fusion-powered system can be, and more importantly, what kind it cannot be. For laser defense, fusion changed the power equation entirely. The reason today's system sit at hundreds of kilowatts is electrical supply. With fusion's effective abundance, megawatt class output becomes routine, and gigawatt class output becomes thinkable. At those levels, atmospheric attenuation and plasma shielding cease to be hard barriers. They become loss factors that brute force can overcome. Energy alone, however, is insufficient. A human being cannot aim at the Mach 10 maneuvering target. The targeting is the second key, and the technology is artificial intelligence, but a very specific kind of AI. The three roles are required, and the defense AI must perform all three in milliseconds. First, real-time tracking and trajectory prediction, solving the missile instantaneous motion equation while it actively maneuvers. Second, adaptive optics, continuously deforming the mirror surface thousands of times per second to compensate for atmospheric distortion so that energy concentrates at that point rather than scattering across our area. Third, threat prioritization for multi-warhead attacks, deciding faster than human reaction, which submunition is most dangerous and must be engaged first. This AI does not need to be general. It does not need to write essays or pass legal exams. It needs to solve a small set of physics and image recognition problems with very high fidelity, very fast. The architecture is closer to a flight control computer than to a chatbot. Two further properties matter. The system runs on a network that is physically disconnected from external infrastructure. No cloud dependency, no remote authentication. no foreign software stuck at the kernel level. And the inference hardware ideally is designed and manufactured within the operating polity. These are not nationalist preferences, they are sovereignty condition. A defense system that another government can disable by cutting a cable or revoking a license is not a defense system. It is a permission slip. Even with fusion in the properly bounded AI, two problems remain. The Earth is curved. A ground-based laser cannot fire at what is below the horizon. And atmospheric physics still impose weather-dependent attenuation, even at the megawatt level. Solving these requires changing the geometry of the system itself. The default architecture currently being pursued by both the United States and China is the most obvious and the most expensive. Launch the entire system into orbit. Each satellite carries its own miniaturized fusion source and its own laser apparatus. Several hundred satellites from a constellation, total program cost runs to hundreds of billions. This approach has a fundamental contradiction. The economic case for laser defense rests on cost asymmetry, a few dollars per shot against a $1 million threat. If the platform itself costs hundreds of millions per unit, that asymmetry is destroyed before the first shot is fired. The defender is back to subscription economics, only now in orbit. There is also a survivability problem. A satellite running an active fusion source emits thermal signature that any competent infrared sensor would detect at hundreds of kilometers. The defender's most expensive asset becomes the easiest to find. A different architecture is possible, and physics does not care which nation implements it. Keep the heavy, hot, expensive components on the ground. Place only the mirror in orbit. The flow is straightforward. Ground-based fusion power laser source fire high energy beams upward to mirror satellite in low orbit. The satellite is, in effect, a precisely angled relay. It receives a beam and reflects it onto the target. Energy generation, fuel handling, cooling, and the maintenance all stay underground, where they are tractable. What goes into orbit is light, cold, and largely passive. The advantage compound. Cost per orbital unit drops by an order of a magnitude or more. Because the mirror is the only payload, this is restore the economic asymmetry that justified the system in the first place. Redundancy follows automatically. If one mirror is destroyed, others continue functioning, and the replacement is cheap. The weather risk distributes across geography and distribute the ground station across a sufficiently long axis. Any nation with a geography is eligible, and the probability of all sides being weathered out simultaneously approach zero. The snow in the north does not matter if it is clean in the south. Power consumption, because asymmetric in time, standby mode runs at a low output and low thermal signature. The full output is reserved for actual engagement, and most of the time the system is hard to see when it need to engage, decisively. Adversary surveillance is forced to choose between watching the satellite continuously, revealing their own asset and missing the moment of engagement. The mirror itself depends on the class of material engineering, and that is not yet broadly distributed. Metamaterials are engineered structures whose optical behavior is determined by geometry rather than chemistry. They allow reflectors that are linear, more thermally tolerant, and directionally selective in ways that no conventional polished metal can match. The pointing mechanism, aiming the beam to within a fraction of an arc second across hundreds of kilometers, depend on adaptive optics traditions developed for ground-based astronomy. Both capabilities exist identifiable research lineage. Neither is intrinsically national. They are, however, expensive to assemble in one place at one time. It is not for me to claim superiority for any one nation's industrial-based. The material science merely permits this approach, where a particular density of a capability already exists. The argument is not we are exceptional, and the argument is the configuration is feasible, where the prerequisites are present. The deeper point is that this architecture is not the brute force solution. It does not match weight with weight or armor with armor. That it works by making the adversary's attacks alive in the wrong place, by deflecting rather than absorbing. This is the different design philosophy. It is also not coincidentally more compatible with a non-aggressive posture. A system optimized for deflection cannot easily be repurposed as one optimized for projection.
Imagine a nuclear warhead tearing through the upper atmosphere at like Mach 20. Now, imagine stopping it, but not by launching another interceptor missile. You do it with a silent, invisible beam of light that basically tricks the weapon into destroying itself.
Yeah, it really is the ultimate high-stakes engineering problem. I mean, you're dealing with energies that want to completely destroy the machine creating them.
Right, which sounds impossible. Welcome to today's deep dive. For you listening, we're pulling from translated excerpts of Kibyu's Shield of Light scripts to explore the real blueprints behind fusion-powered laser defense systems.
It is a fascinating set of documents.
It really is. So our mission for you today is twofold. First, we need to figure out if this tech stack is just press release vaporware. And second, answer a very real public anxiety, like what actually happens to the physics of a nuke when you hit it with a megawatt laser?
Well, let's tackle that skepticism first.
Yeah, because I look at these sources, and the phrase megawatt-class laser jumps out. Pushing that much energy should instantly melt the firing mechanism, yet the literature claims they are using diamond substrates.
I hear that and just think of inflated defense budgets. Like, why are we bedazzling a weapon system?
Well, it's not for aesthetics. Artificial diamond is a strict structural necessity here. It actually transfers heat roughly 5 times faster than copper.
Oh, wow. So it's basically just a massive heat highway.
Exactly. When you generate a beam of that magnitude, the diamond substrate acts as a huge heat sink. It pulls extreme thermal loads away from the diodes. I mean, without it, the system incinerates itself before firing a single shot.
Okay, so the laser actually survives its own ignition, but generating the beam is, only half the battle. Because if you shoot a laser of that power through the atmosphere, you hit thermal blooming, right?
Yeah, the air heats up.
Yeah, the air heats up, distorts the beam, and suddenly your ultra-precise sniper rifle turns into, like, a blurry flashlight, which is exactly why the system's aiming mechanism is so vital. It relies on a combination of metamaterials and adaptive optics. Metamaterials are these engineered geometric structures that can perfectly manipulate light without the bulk of traditional heavy mirrors.
Right.
But the real workhorse against that atmospheric distortion is the adaptive optics.
Which is borrowed from ground-based astronomy, if I remember the text right.
Precisely. To punch through that atmospheric fog, the system physically deforms its mirror surfaces thousands of times per second.
Thousands of times a second. Wait, really?
Yeah, it reads the thermal blooming ahead of the beam and actually alters its own shape to counter the distortion in real time.
But I mean, calculating those deformations thousands of times a second while tracking a hypersonic target, wouldn't traditional silicon chips just lag out or melt under that processing load?
They absolutely would. And that is where integrated photonic computing comes into play. We are basically swapping electrons for photons.
So using light instead of electricity.
Yes. Processing data with light means near zero friction and near zero heat generation. The AI can calculate those intercept trajectories and mirror deformations in just milliseconds.
Okay, so we have the beam, we have the aim, and we have the processing speed. I feel like we've successfully separated the vaporware from the reality here, but let's get into the public anxiety piece.
The big question.
Yeah, the system spots a fully armed nuclear missile, it fires. Doesn't hitting a nuclear warhead with a high-powered thermal laser just trigger the apocalypse early? Like, you zap it and kill everyone below anyway.
It is a super common fear, but it really ignores the mechanical reality of how a nuclear weapon works. Yielding a nuclear blast requires mathematically perfect symmetrical compression of the radioactive core.
Wait, let me make sure I'm picturing this right. So a nuke isn't just a balloon waiting to be popped by the laser.
No, not at all. It is more like a highly complex Swiss watch. The photonic AI specifically targets the missile's altitude-based fusing logic. That's its brain.
Ah, I see.
By burning out that arming logic, the conventional explosives that surround the nuclear core end up misfiring asymmetrically.
Right, so because the conventional explosives go off out of sequence, the core's geometry is just destroyed rather than perfectly compressed.
Exactly. You get what physicists call a fizzle.
A fizzle.
Yeah, the physical structure breaks down entirely before any critical mass can be achieved. It's essentially a dud reaction. You're left with a broken machine, not a nuclear blast.
Well, that prevents the nuclear yield, which is obviously great. But we are still talking about a shattered warhead scattering its radioactive core, right? I mean, you've essentially just created a high-altitude, dirty bomb.
And that is the secondary threat. It's exactly why intercept altitude is the most critical variable for civilian reassurance. If you shoot down a cruise missile in the lower atmosphere directly over a populated area, toxic debris still rains down.
Which perfectly explains the orbital mirror satellites detailed in the texts. The system doesn't shoot straight up from the ground. It bounces the beam off orbital metamaterial mirrors to intercept the missile way up in the stratosphere, or even out in deep space.
Right, and that altitude ensures the radioactive debris either harmlessly burns up upon atmospheric reentry, or it diffuses so widely that it never poses a concentrated threat to the surface below.
It really fundamentally changes how we look at planetary defense. You take this apocalyptic threat and reduce it to a solvable equation of deflection and altitude.
It's reassurance through accuracy.
Reassurance through accuracy, I like that. But it does leave you with a deeply unsettling question to mull over. If these metamaterials can make orbital mirrors thermally invisible, and lasers can dismantle threats silently at the speed of light, will the major conflicts of tomorrow be fought and resolved entirely in the dark without any of us ever knowing an attack took place? Definitely something for you to think about.
There is a question that any serious treatment of this technology must address. It is not, can it be built? That answer has a technical answer. The question is, who can be trusted to operate such a system without converting it into something else? The default Western answer is procedural. Any sufficiently allied state may have access. Trust is treated as exhausted by alignment. I want to suggest that the question is more demanding than that. Begin with the philosophical layer. The dominant operating system of contemporary international politics is binary: allies and adversaries, civilization and barbarism, good and evil. This is sometimes traced to Christian theology, the sometimes to Cold War habit. It runs deeper than either. The German legal theorist Carl Schmitt formalized it as a friend-enemy distinction, which he held to be the irreducible essence of the protocol. Schmitt was wrong on the descriptive question, and not all politics has been structured this way, but correctly identified the operating system that the West has in fact adopted. It is worth nothing that this OS was not always dominant, even within the lineage that produced it. The original teaching attributed to Zoroaster, the source most often cited as the origin of cosmic dualism, was significantly more interior than the political dualism that later emerged. The original conflict in those texts is between order and chaos within the individual conscience. The Persian Empire that operated under that influence was, by the standards of its era, notably tolerant of religious plurality. The Cyrus released of the Babylonian excited Jewish population, often cited as a moral landmark, is a direct expression of the tolerant operating system. What we now call the Western dualistic OS is not Zoroastrianism. It is what the Roman Empire and its successors made a much milder source material. Imperial governance has structured reason to prefer binary categories. They are computationally cheaper than nuance. A friend or enemy runs faster than complex regional actor with mixed interest. Over centuries, the cheaper algorithm win by attrition, regardless of its accuracy. The relevance to the shield of light is direct. A defense system run by a policy operating on binary category will inevitably be deployed binary against the enemy on behalf of the friend. Such a system does not produce neutrality. It produces escalation. The hardware does not need to be modified. The default deployment logic is already aggressive. A defense system run by a polity that has not internalized the dualistic OS as deeply has different default behavior. There exists civilizational lineage not racially or geographically determined by the historical real, in which the dominant heuristic is not destroy the other, but restore the equilibrium. In Western theological vocabulary that crosses analogs might be the Hazecast contemplative tradition or certain readings of a moralistic stillness. In East Asia, the relevant lineage runs through several streams. Certain current of Mahayana Buddhism, the Confucian preference for ritual restoration of punitive escalation in the Japanese culture practice that English typically inadequately translates as harmony. This is not Japanese exceptionalism. The OS in question is a non-dualistic civilizational protocol. The several lineages have approximated, none have perfected and any of them could in principle implement more deeply. It is, however, an empirical fact that the parties are currently most committed to a dualistic confrontation are the parties least suited to operate a deflective defense system without converting into an offensive one. This raises a practical question that deserves a name. Call it conditional technology diffusion. Where access to the IAEA supervised civilian nuclear regime was conditional on inspection commitment, access to fusion and laser defense capability could possibly be conditional on the different tests that demonstrate the behavioral patterns of the operating policy. Not its declared values, those are cheap, but its observable record of how it behaves when it possesses a symmetric advantage. The principle would not exclude any nation by name. It would, however, require any nation to qualify by behavior. Some nations would qualify easily. The others would have considerable historical work to do. There is a corollary that I will state plainly and then leave alone. The principle of conditional technology diffusion is not a license to interfere with other policies. Independent development of equivalent capabilities. If a sovereign nation pursues fusions or directed energy defense through its own scientific base, that is not a matter for external sanction. The only thing this framework license is discipline in one's own technology transfers. Restraint in what one shares is not the same as restraint imposed on others' research. The deeper claim, then, is that the shield of light is not the weapon. It is a structured device for insulating a civilization from the negative feedback loop of binary conflict, so that something other than escalation remains possible. A clean room requires walls. The walls are not aggression. The walls are what allow the work inside the room to continue. The technical case is the easier part. The harder part is whether any actual government can sustain the political will to implement it. The budget first. A reasonable estimate, assuming fusion development proceeds a 5-year timeline, place the remaining system cost at roughly 5 to 10 trillion yen, approximately 30 to 70 billion dollars at the current exchange rate, over a decade. The ground-based laser station, mirror satellite in the dozens, integrated AI command network, and ongoing maintenance. As a single annual line item, this is impossible. As a 10-year program at 1 trillion yen per year, it is comparable to a fraction of Japan's existing defense budget. Large but not unprecedented. These structural gap separate this trajectory from current Japanese defense planning, and they are worth naming clearly. The first gap is between consumable munition and energy weapons. Existing planning still emphasizes large purchase of one-shot missiles, mostly American, some domestic. The proposed direction involves a paradigm shift toward laser-based defense, where capital expenditure is highly, but operational expenditure approach there over the system drive. The two procurement philosophies are not compatible at scale. One of them will eventually displace the other. The second gap is between integrated dependency and autonomous operation. Current Japanese defense systems are deeply integrated with American GPS communication and early warning networks. Official policy remains alliance-based deterrence. The proposed direction requires sufficient operational autonomy that system continues functioning, even if external networks become unavailable. Whether through political change, technical failure, or strategic disagreement, this is a different posture, and it cannot be achieved by purchasing alone. The third gap is autonomy out of the AI itself. Japanese defense doctrine, like most Western doctrines, currently mandates human-in-the-loop authorization for kinetic action. The interception of Mach 10 hypersonic threats does not permit a meaningful human-in-the-loop. The decision must be made by the system in milliseconds on the basis of physical data. Resolving this gap requires explicit legal authorization for narrow defensive automated engagement, and not a license for autonomous offense. But the admission that some classes of defense are time bounded below human reaction speed. The current Japanese administration in office since late 2025 has shown awareness of all three gaps. Public statements have linked fusion development explicitly to defense applications, committed to a shift from purchasing defense toward manufacturing defense, and accelerated planning for domestic satellite constellation. The framing here matters. Critics describe the administration-controlled cooperation with the United States as accommodation. A more accurate reading is that the cooperation is being maintained as a time purchase, the period during which Japan completes the technical foundation for genuine independence. Independence cannot be declared on a press release. It must be first, then practice. Whether this trajectory survives a political transition is frankly the largest single risk to the program. Mega projects do not survive policy reversals. The technical answers to "can the shield of light be built?" is yes. The political answer to "will it be?" depends on community that no one can guarantee in advance. For viewers watching this experiment from outside Japan, several signals are worth tracking. The pace of fusion development, whether private fusion programs in Japan, several are now operating at a non-trivial scale. The rich industrial demonstration on a 5-year horizon was slipped to the conventional 10 to 15-year industry consensus. The slippage matters because it determines whether the larger architecture is technically possible in the relevant decades. The integration of materials, semiconductors, and photonics, whether the domestic semiconductor program now under the construction in northern Japan reaches its planned 2-nanometer production timeline, and whether it integrates with a photonic computing initiative that technically necessary for the proposed AI architecture. These are not separate stories. They are the same story told in different sectors. The behavior of the current Japanese administration, whether the rhetorical commitment to technology sovereignty translates into actual reallocation of defense expenditure away from imported consumable and towards domestic capability. Budget documents are more reliable than the statements. The emergence of the framework I have called conditional technology diffusion. Whether Japan, in any official document architecture, articulate the position on technology transfer that distinguish between alliance access and qualified access. Based on the behavioral criteria, this would be a significant departure from the current diplomatic practice and would almost certainly be controversial. They watch for the language to appear, perhaps initially in academic or cursive official venues before it appears in policy. Finally, what's the discourse itself? The most important question is not whether any specific technical milestone is reached on time. It is whether to broader public conversation in Japan and outside it. Developed a vocabulary to describe what is being attempted. Civilization can fail at a technical project and still have advanced an idea. A civilization can succeed technically and have the achievement misread by itself or by others as something it is not. The vocabulary matter. The technical fragment already exists. Diamond substrate, metamaterial, photonic computing. The fusion energy at this decreasing distance from industrial reality. Adaptive optics with several decades of astronomical heritage. Each fragment is real. Each in isolation is unremarkable. What is missing is integration, not technical integration. That is an engineering problem. And engineering problem gets solved when sufficient resources are committed. What is missing is political and civilizational will to commit those resources to coherent defensive posture rather than to incremental purchase of someone else's hardware. Whether that will materialize is an open question. It is not impossible one. Then components are present. The historical moment, a clear demonstration that the existing defense paradigm is economically broken, is unusually favorable. The political configuration in Tokyo is, at this moment, aligned with direction to travel. Then whether this experiment succeeds matters beyond Japan. It matters because the alternative paradigm are being demonstrated. A deflection rather than projection, neutrality rather than alignment, conditional diffusion rather than the universal sale is something the international system has not seriously attempted in its current form. If it works, it is a model. If it fails, the failure mode themselves will be informative. For those watching from outside, the most useful disposition is patient attention to structural indicators rather than of new cycles. The interesting question in this domain are decade long, not week long. Thank you for following the 6-part inquiry. The next series moves to a related question: how to identify in real time the leadership pathology that convert defensive technology into offensive one. We will return to it. I am Cube. Until next time.